I'm Barik from Uber, and this is the work that we worked on Swift to optimize protocol performance. Just to give you some background on Swift, those who do not know, this is a language that is gaining in popularity, in particular in the iOS application domain, where mobile developers are developing apps for iOS. And this language has a pretty neat, bunch of neat features. And I mean, if you compare it with respect to its competitor, which is Objective-C, Jan already talked about some of the, bad things about Objective-C, and no wonder that this language is actually picking up popularity. And Uber is actually one of the early adopters of this language, and in fact, there's a talk one of the Uber engineers gave was to improve the crash-free rate of Uber app. We had to take the Swift route. So some of the features of the language include type safety, which is very important for us, and it's statically typed. And memory safety is another important thing that is very useful to us. And it also has other features like generics, closures, and protocol-oriented programming, which is where I'll spend most of my time optimizing it. This language is also built on top of LLVM, so it has good performance in some sense. It has an active open source community which helps in contributing code out there. Okay, so we have a bunch of Uber apps at that is targeting both iPhone and Android. In particular, for the iOS side, the Rider app, which is used by millions of people in the field, is mostly written in Swift, and it consists of about 1.7 million lines of code, out of which 83% is Swift, remaining are Objective-C. It has I don't know how much Swift, but it has around 200 modules, and each module has some pieces of functionality that is embedded with respect to it. And this code heavily uses protocols, generics, and structs. And in fact, we use roughly close to 10,000 protocols. And it's critical for Uber and Uber's business that the app is reliable, and you don't see many crashes in the field. At the same time, the touch performance of your Uber app must be very good, so that the customer is satisfied with it. Keeping these two in the goal, I'll talk about the optimization of the protocols for Swift. Okay, so just to give you some introduction on protocol-oriented programming in Swift. And Swift goes in the direction of composition as opposed to inheritance. So you define a protocol with a small set of functionalities that you compose to make a bigger set of functionalities. So inherently, you can think about it like you try to introduce less bugs by putting functionality in smaller protocol types. And so what is a protocol in some sense? It's a set of methods and properties and their associated type requirements. And any type can conform to this protocol, and you can even conform to more than one protocol. Okay? Both value types and reference types can conform to a protocol. And so Swift makes this distinction between class protocol and non-class protocol. And here is an example that shows a class protocol, and another example in the bottom that shows non-class protocol. So the only difference here, if you can see, is that any object implementation or inheritance you see from for the drawable, and that defines it to be a class protocol, which is essentially a reference type, and can only be implemented by a class type. You can see there on the top, and on the bottom it's a value type. It could very well have been a class type as well. So as long as you put an any object, it's a class protocol. If you don't put any object, it's actually non-class protocol. So what is interesting here is that since a protocol, if it is a non-class protocol, both value types and reference types can actually implement this protocol. Okay. And these protocols also, like like vtables in C++, you have dynamic dispatch, and this comes through a protocol witness table. Okay. Um, Looking at how protocols are used and primarily classifying them, we see at Uber many of these protocols are actually used for test mocking. And it's an interesting feature because in order to test your code, you don't want to really go into do the database operations. You just want to mock those database operations or networking calls. All these you want to mock as much as possible. And this is one way. What you do is you define a protocol and you have two implementations. One that is the real implementation and one that is the fake implementation that actually fakes all the network calls, DB operations, and IO operations. And this makes your unit testing very easy. Okay. And there is a tool that Uber has released called Mokolo, and that actually automatically generates these implementations for you. Okay. So here is an example. You have a protocol called location protocol, and that's mockable. So you define it like through comments as mockable, and you provide the original implementation as location. That is a location that conforms to location protocol, and it has some method implementation, and it returns the original value. It could be doing some network calls as well. I'm just returning some value here. But if you run through these tools, it'll generate a mocking version of that particular protocol, and the mocking version can very well just return and say I'm returning nil. So you're mocking the entire process there, right? Okay. So what's the complexity here? So yeah. So if you look at these protocols, you're basically looking at two implementations. Now, if I were trying to release this code into production, I'm not really interested in the mock. I'm only interested in the real implementations, right? So the mock part of the code, even though it is there, I don't care about it, right? So I really need to figure out a way to strip these mocking versions and only have one-to-one correspondence between protocol and the concrete type, and then I can go ahead and eliminate as much as the dynamic dispatch as I have. Okay, so that's the goal of this work, and I will see how that manifests in Swift and why it is complicated. Okay, so just to give another introduction, so just the flow of the Swift compilation. Swift files are processed by the Swift front end and produces Swift AHT. From there, you perform a bunch of semantic checks. You generate an IL, which is intermediate language in Swift, which is called SIL. And you perform high-level optimizations in this SIL before you generate code in LLVM, and from there on you apply a bunch of LLVM optimization, and subsequently you generate binary. Okay, so what happens when you have a protocol? Okay, so let's take the same example. I have a protocol drawable that has a method requirement as draw, and I have a value type which is a struct and line that implements the drawable protocol, and it has 4 fields, happens to be like 2 coordinates, and then I have function draw. I have eliminated the implementation for it, and then later on I go and create a val which is of protocol type, and I assign it to the line object that I create. Okay, so now what happens when I create an object of line and then assign it to the protocol variable? What happens under the hood in the code generation? Okay, so that's where whole like the complicacy comes in. So since this is a protocol variable, we don't know whether it will hold a value type or a concrete type, reference type. So what Swift does is generic. It uses a generic container approach, which is called existential containers, and which are inspired by existential types. That is very well known in the community. And so what do these existential containers contain? They're allocated in the stack, first of all, and they have, like any vtable dispatch, they have protocol witness table right there in the bottom. And in the top, you have 3 words to keep. If this was a value type, then you want to keep these values. If they fit into these 3 words, then you keep the values in line here. If they don't fit into 3 words, then you create a memory for them in the heap, and you maintain a pointer to this in the first value buffer. And then you stick in a value witness table that manages this allocation of the object in the heap. And so this is exactly what happens in the line case, because you had 4 fields which happen to be double, and they don't fit into your value buffer. So you essentially created an object of line in the heap and then keep the pointer in the value buffer. Now, I mean, if you look at it, in this particular example, if I knew that line was the only um, struct that was implementing the drawable, I could do something. I don't need all these existentials that you create on the right hand side. Or there are cases we'll talk about if line was passed as an argument to a function, what can I do about it? Okay, so all these overheads actually blow up not only the code size but also the performance, because you have to go through all these indirects and maintain this existential containers. Okay. So yeah, I talked about all these overheads. So one more overhead that I want to add is that these protocol witness tables that are attached for every protocol actually incurs some amount of cost when you try to start up your app in the mobile phone, because these are data structures that have to be preloaded as part of the pre-main process. So that consumes some amount of time in loading these witness tables. Okay. So the question we asked is, how do we optimize away these existential containers statically and their overheads? Okay. So I'll talk about three approaches and three different transformations and analysis as part of my talk. One is soul type, which essentially looks at one-to-one conformance between protocol and the value or the reference type. And this is similar to the type hierarchy analysis that we have seen in past work. The second one is a little tricky if you pass an existential as a parameter to a function. Now, I'll talk about what kind of transformation we do to optimize that. And then the last one is to do a data flow analysis within a procedure, nothing fancy, no interprocedural analysis, and still be able to determine what the concrete value or concrete type that gets propagated in the code, and then be able to eliminate all the existentials that appear in the code. Okay. So before we do that, since we are working at a cell level, we really need to reason about the semantics of the operations that appear at the cell level. So here are some of the instructions that are relevant to the existential containers, and I'll briefly talk about their semantics here. So these, like alloc stack is allocating a location in the stack, and store and copy adder essentially manipulate memory. Okay. Then I have init existential ref and open existential ref, which essentially operate on the class protocols that I was talking about. Okay, and they correspond to class containers in some sense. So init is essentially creating an existential container for reference types, and open existential ref is actually opening that existential container to get you the underlying data reference that is there in the existential container. Okay, then the two which are init existential adder, these are dealing with address types. Address types is essentially saying that I don't know what you are holding in the container. You could be holding a value or you could be holding a reference, in which case it's essentially representing the non-class protocols. And then witness method, which essentially does the lookup of the method. Okay, and so to provide the semantics of it, we essentially maintain a state consisting of three maps. And if you start from the bottom right there on the variables to value address, that's the row mapping. I mean, if you look at alloc stack, it essentially maps from the variable xi equal to alloc stack t on the left hand side there, and you keep a mapping from xi to the memory that is allocated by alloc stack. Okay, and similarly for existential ref, you essentially create a class container using CL container k and a, and k is essentially representing the protocol witness table. A is the object that we are trying to store into the existential, and then you map that to your xj, and those are the mappings that are kept in row. Sigma is another mapping that is used for init existential adder that has multi-sequence initialization in the cell level. And alpha is essentially using some kind of notion of when you try to open an existential ref or adder, you have what cell defines as called an archetype. And archetypes have static IDs associated with it, so that the compiler, when it looks at the witness method, be able to associate that ID to the protocol witness table to do a method lookup. Okay. So, and I'm in the interest of time, I'm not going to talk about the op container, which essentially deals with non-class protocol or called opaque containers. Okay. So, so moving on, once we have the semantics of it, let's try to apply the soul type. Okay, this is I talked about as a type hierarchy analysis. So in this example, we already walked over it. So let's say I have a local as an argument passed to the function draw it, and I call the draw function on it. Okay, so if you look at the code and if you can reason about it in Swift, that the protocol and the conforming type are actually internal, which essentially, and so this goes back to Swift's access levels. If they are accessed within the module, they're not exposed outside the module, then you derive the fact that only line implements drawable. And hence you can do a whole module optimization, which essentially Swift basically looks at the entire module, and then devirtualizer. And the way you do it is basically inserting a cast. Once you open the existential adder, you insert an unconditional address cast to cast that this argument that is coming into the function is actually a line object. And then subsequently, devirtualizer will come in and then replace the virtual method call, which was originally a witness method call, and replace with a call to lines draw method. Okay, this is very well known. Okay, but I think the bigger concern here is that, you know, if you can look at this code, I put the cast here, but I haven't done anything with these existentials. The existentials continue to stay, and they can blow up your code and, you know, hurt your performance as much as possible, right? So the next technique is, you know, I'm going to talk about is Param. So let's look at a bit more complicated code. Okay, that's a lot of code there, but this is standard BucketSort code written in Swift. Okay, so what it essentially has is, you know, has a protocol called sorter, and sorter provides a generic sort implementation. And then we have insertion sorter, and that is one kind of sorter and provides real implementation of the sort code here. And then you have buckets, which are sortable buckets, and the arguments are sortable. I mean, integer is sortable, so you can have integer of bucket. And then the sort algorithm on each bucket under the hood calls these, you know, sorter algorithms that you have. Okay, and then finally you have BucketSort that is exposed outside through the sorter and the buckets and the elements, and you take each of the buckets and then you sort. You put the elements into the buckets and then you sort individual buckets and then combine them together to return the results. So in this case, what is happening is that if you look at it very carefully, sorry, I think. Okay, yeah. So if you look at the sort routine, that is invoked through a dynamic dispatch here on algorithm, which happens to be a sorter. And if you look at the code, there is an insertion sorter being passed all the way down there. So if you knew that the algorithm was actually insertion sorter, I mean, in this case, I just showed you insertion sorter. You could have another implementation as well, right? So you could have, like, you know, maybe, you know, some quick sort or something else, right? So if in this case, you have a dynamic dispatch on the algorithm.sort, and that prohibited from specializing the sort method, because you don't know who your dispatcher is. So Swift's existing generic specializer actually gives up, saying I won't specialize this code even though it's an array of integers. So now what happens is that this code is very slow. Okay, this is like 20x slow. 10 million array sorting code takes huge amount of time. Okay, so we know here, if you did a little bit of, you know, analysis, you will know that the insertion sorter is the sorter that I'm using here, and hence I can propagate that fact all the way down the call chain, and then use that to devirtualize that sort call, and hence all of a sudden generic specialization will come and say, oh, I know everything now. I can propagate the integer type all the way down. Okay, and so one thing to note here is that we want to do a transformation that actually allows, I mean, we don't want to do interprocedural analysis, right? We want to do something that allows us to be able to devirtualize this sort method call. Okay, although you can try and see, you know, try to do some amount of, and inlining can eliminate this kind of a thing. If it was not a generic code, you could have done, you know, way down in the call chain, you can keep on inlining, but then there is some amount of restriction on how much inlining you can do. Okay, Oh, okay. Yeah, so I think in the interest of time, so this optimization is essentially what it does. It's under the hood. It creates a protocol constraint generic function, and has an outer function that has an inline attribute to be able to be inlineable in the caller context, and hence you can now specialize this particular function with respect to the insertion sorter we saw earlier. Okay, and then all of a sudden you will see a very clean up code and specialized code, and that's 20x faster. Okay, that results in a 20x faster. You specialized everything. The next one is the data flow analysis, which is basically if you have within a function, a container contains two different values in two different paths. Then in one of the paths, if you change something, in this example, you can see here, I'm changing A2 to A1. Suddenly, even though you are able to devirtualize it using your class hierarchy analysis or type hierarchy analysis or soul type, you are not able to optimize away the existentials. Okay, and this is where we propose a data flow analysis, forward data flow analysis within the procedure to be able to propagate the mapping from the containers or the abstract containers to the real values they are holding. That goes through a variable to abstract container mapping and container to the concrete values, and then we at the point of the witness method, if we know one particular value or one particular type, we can devirtualize it. And the other thing that we do is that even though it is more than one value, what you can do is you basically try to see if you can keep the program in SSA form with the concrete values, and then optimize away all the existentials. Okay, and this is what it happens. Finally, if you apply this optimization, you will see that you no longer need any kind of existential containers. Okay, and this basically shows our high-level implementation, and you can see that we have touched a number of components of Swift, in particular doing this data flow analysis and also the transformations. Okay, so here is the result from a set of benchmarks from the Swift benchmark suite, and this is actually it's very hard to find protocol heavy benchmarks out there, but it turned out there were 6 of them that actually heavily used protocols, and with all the transformations that I talk about. And what I didn't also talk about is the interoperability between these transformations, which is there in the paper. We can see that on an average we can get like 1.6x speed up on a MacBook Pro compared to the baseline of Swift. Code size impact, this was one of the goal also. We did see for some of the benchmarks code size reduction, but for BucketSort we saw a code size increase, and that was because the BucketSort method which we were specializing was a public method, and its original generic version was retained in the code. So once you change the access level of the method, you will see a reduction in the code size. From the Rider app, this was pretty surprising to us. We did an experiment on the iPhone 6s, although we had to backport our optimization. We saw a startup improvement of 12%, but the core spans, which were like the performance spans of the Uber app that was introduced by the developers by themselves, we saw like 6% all the way to 55%, depending upon how much protocols they are actually using under the hood. And we didn't see any increase in the binary size, because once you statically devirtualize, there is a potential that you could be inlining everything, right? So, but we did see some like 1.7% or 1.4% reduction in the binary size for V7 and V64. And there is a bunch of related work, in this space. I think the way we differ is like we apply some of these optimization, and also extend that to Swift in particular, because there are some more challenges in the Swift. Conclusions: using protocols is a good idea. It's a good software engineering practice, and protocols do introduce some overheads. And I talked about our approaches of eliminating these overheads. And some of these transformations, Soul Type, Param, are already part of Swift 5, and we are in the process of doing, transferring the data flow analysis. So yeah, thank you. And this is the Uber disclaimer. I'm happy to take any questions.
We have time for exactly one question. I had a simple question. You mentioned we don't want to do whole program analysis.
Yes.
I wonder why. I mean, this is statically compiled, and once you compile, this is run on billions of cell phones. Why you don't want to do static
Okay,
compile?
so okay, first of all, there is no way Swift in Swift to do whole program analysis. What is available is like you break up your code into different modules, and there is a whole module optimization that you can do, but not across programs. And this is one of the work that one of my colleague and I are working on, is to enable whole program optimizations at the Swift level and see what its impact is. But that's different talk. But today, as it stands, there is no whole program analysis or optimization being done at Swift level. Okay.